let's now discuss how we test hypotheses. So we already know how to formulate them, how to choose a significance level. We know different types of hypotheses, but how do we test them? So when you solve a hypothesis testing problem, you are always to have a statement, a proposition, a theorem, as we say in mathematics, of this kind you see now. So you are to have a statement that states that if HO is true, if the null hypothesis is true, then a statistic, that means a random variable that is a function of observations, a given function of observations, has the given distribution law. And so here the function g must be given and the law distribution must be given. So you are to have the formula for this t, for this random variable, and you are to have the distribution, either the name of the distribution, like for example exponential distribution with parameter 2, or normal distribution with parameters 0 and 1. So or the PDF or the CDF. So this law distribution is to be clearly defined here. So either by the name and the parameters, or by the PDF or by the CDF. So this theorem, this proposition, is to be formulated and proved. So, but the good news is that the one who formulates and proves this theorem is not is not yourself. So it is the one who proposed the test for our hypothesis. So I mean that, so when I say that the following statement should be formulated, I mean that if you open a book on hypothesis testing, a textbook for example, and you choose a test, a type of hypothesis testing problem, and there the test is described that is used for these type of problems, and there this description of this test always includes a proposition of this kind. So it is necessary to formulate and prove such a proposition for those who are proposing some new tests for hypothesis testing problems. So this T is called the test statistics, the test statistic. So as we know that the term statistic is used for any random variable that is a function of observations. And so as the T is a function of observations, it is called the test statistic. So statistic of the test that we will use to test a hypothesis. And so this function, this formula that is used to find T, so it is such a formula that one can make assumptions which of the two hypotheses is more likely to be true. So like for example, when you just have a look at the formula of the test statistic of a given test, you understand, so for example, values of the test statistic that are close to 0 are in favor of the null hypothesis, and values that are far from 0 are in favor of the alternative hypothesis, or vice versa, something like this. So the test values of the test statistic give you some information on which of the two hypotheses is more likely. Okay, so then you calculate the value of t. So t is a function of observations. You have the observations. So in mathematical statistics, in all problems of mathematical statistics, we have the observations. So, and you calculate the value of t, observed value of t, sometimes they say, and you are looking at this number you have just calculated, and you try to understand. So whether you are going to believe that what you see is a realization of a random variable that follows the law distribution or not. It's better to believe or not to believe. So how you can choose whether to believe or not to believe. Let me explain this with an example. Let's say that I go out of this room and I come back in 5 minutes and I show you a sheet of paper with a number, and I ask you, do you believe that this number I'm now showing you is the height of the first person I have just met at the corridor? So this is the question, and you are to choose whether to believe me or not. For example, I say, if you guess, I'll pay you, I don't know, 100 rubles. So it's better for you to answer than not to answer. So your answer obviously will depend on what number I will show you. For example, if I go back and if I come back and I show you number like 203, and I ask, do you believe that this is the height of the first person I have just met at the corridor? So you will probably won't believe. Why? Because there are people of such a height, but they are very rarely met. So they are very tall people, and it is very improbable that the first person I have just met at the corridor is a so tall one. So you will probably say, no, I don't believe, as you know that this is a very improbable situation, that the first person you will meet will be such a tall person. And so do you if I show you number like, I don't know, 151, for example. You will also say, oh, this is a kind of a very short person, and it's hard to believe that the first one was so short. And if I show you a number like, I don't know, 165, 171, and so on, you will believe me, as you know that these are common heights of people. So people of these heights are very common. So it's very just easy to meet a person of this kind. So it's quite probable that the one I have just met first at the corridor has the height equal to this value. So how we can generalize what is happening here? We can say that, so you have an idea of a distribution of the height of a random person. So you know that there is a random variable, the height of a random person, the height of the first person you meet at the corridor. This is a random variable. This random variable has some distribution. Maybe you don't have the PDF or the CDF of this distribution just in your head, but you have some general idea of how this random variable is distributed, and you know which values are more probable, more often, more frequent for this random variable, and which values are less probable, less often, less frequent, and which values are almost impossible, and which are absolutely impossible. So you know that it is impossible to meet a person with his or her height equal to 400 centimeters, for example. And when you answer my question, when you choose whether to believe me or not to believe, what do? You are trying to understand. So if this value I'm showing you, is this a highly probable value, a likely value of this random variable or not? And if you see that what I'm showing you is a highly probable value, you say, I believe you. If you see that what I'm showing you is a very low, so not so very probable value, rare value for this distribution, you say, I don't believe you. So this is the idea. Here we do the same. Here we are looking at the number that is the realization of the t statistic, and you're trying to understand, is it better to believe or not to believe that t follows the law distribution? As in my example, where you are trying to understand whether it's better to believe or not to believe that what I'm showing you is somebody's height. So this is a realization of the random variable height of a random person. So, and what you need to is to divide the numerical axis into two regions. So the first is the region of highly likely values for the random variable distributed with the law distribution, and another one is the region of unlikely values for this distribution. And these two regions are called acceptance region and critical region, or sometimes they are called region of acceptance and region of rejection, sometimes confidence region and critical region. So there are different names. But still, so you are to divide the numerical axis into these two regions, and so there is just one question. So how to choose the border between these two regions? And so we haven't discussed this yet for my example also. So like, okay, if I show you 203, you say I don't believe you. If I show you 171, you say I believe you. But if I show you, say, 195, it's better to believe or not to believe? And 194, 193, 192, 191. So where is the border? So where it's better to change your choice? So what we are using here in these problems are quantiles. So we know this law distribution, and we can find the quantiles of this distribution, namely quantiles of the levels alpha over 2 and 1 minus alpha over 2. So the most common situation is the one you see at the first picture, so where you have two critical regions, the left one and the right one. And alpha is the significance level, so usually this is 0.05. And when you choose a quantile of the level alpha over 2, that is, so if alpha is 0.05, then quantiles of the level alpha over 2 and 1 minus alpha over 2 are quantiles of the levels 0.025 and 0.975. So what a quantile of a given level is, let me remind you. Quantile of the level beta is such a number that the random variable of your interest takes values less than the quantile with probability beta and more than the quantile with probability 1 minus beta. So quantile of the level 0.025 is such a number that the random variable of your interest takes values less than this number left of the quantile with probability 0.025. And the quantile of the level 0.975 is such a number that the random variable of your interest takes values greater than this number with probability 0.025. So 2.5% for the left critical region and 2.5% for the right critical region. So you say that, for example, you can choose two heights, such height that only 2.5% of all people are shorter than this height, and another one such that only 2.5% of all people are taller than this. Say that 2.5% are shorter than 155 centimeters and 2.5% are taller than 190 centimeters. And so you say what all values between these two quantiles, between 155 and 190, are highly likely values, and values that are less than 155 and greater than 190 are unlikely values. Possible but unlikely. And so that is how you can make a decision here. So this is the thing we do in hypothesis testing problems. There are also options to choose. They usually say one-tailed critical region. So critical region can be either two-tailed, what you see at the upper picture, or right-tailed or left-tailed. And so we will discuss how to choose the configuration of the critical region a little bit later when we will solve examples. So it is difficult to explain this just purely theoretically. So you should just know that there are three possible options: two-tailed critical region, or right-tailed, or left-tailed, or left-sided. So now it's time to make a decision. So you remember that what we are going to do is to choose one of the two hypotheses, either to accept the null hypothesis and reject the alternative one, or vice versa, to reject the null hypothesis and accept the alternative one. So the decision is made as follows. So if t, the test statistic, the observed value of the test statistic you have just calculated, if t falls into the acceptance region, then the null hypothesis is accepted at the significance level alpha. If t falls into the critical region, then the null hypothesis is rejected in favor of the alternative one at the significance level alpha. So that is how we make the decision. So if t is in the acceptance region, we accept the null hypothesis. If t is in the critical region, we reject the null hypothesis. So one may say that what you are saying now is something strange, as you have just shown us this proposition. And this proposition states that if HO is true, then T follows the law distribution. So if HO is true, then T follows the law distribution. So this proposition is the necessary condition of HO being true. Not sufficient condition, but the necessary condition of HO being true. And now, here, you are using this necessary condition as a sufficient one. So you were told that if HO is true, then T follows the law distribution, and here you say, if I believe that T follows the law distribution, I will also accept the null hypothesis. So you treat the necessary condition of HO being true you were given as a sufficient one. And so it's a kind of a logical mistake. So it's not correct, one may say. And so from the one hand, he will be right. Yes, it is not what we are taught to do in mathematics. So we should not confuse a necessary condition and a sufficient condition. So like, let me remind you just, if you have a theorem that if HO is true, then blah, blah, blah. So this is a necessary condition of HO being true. If you have a theorem, if blah, 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 then HO is true, then this is a sufficient condition of HO being true. And so you should not confuse the one with the other. But, so what do we have here? Here, it seems that we are confusing. But actually, we are not confusing when we reject the null hypothesis. So if T falls into the critical region, then this means that we don't believe that T follows the law distribution, and this means that the necessary condition is not fulfilled, is not met, and this means that it's better to reject the null hypothesis. So if we don't believe that T follows the law distribution, then we don't believe that the null hypothesis is true, and so we reject it. So it's everything okay just with the second type of making decision, with the second point here. And so if we fail to reject the null hypothesis, what should we do? We have no other choice than to no other option than to accept it. So if we fail to reject, then we accept, as we have no other reasons to reject after we failed to reject, after we believe that T follows the law distribution. So from a logical point of view, it's better to say not that we are accepting the null hypothesis, but it's better to say we fail to reject the null hypothesis. So this type of giving answer is more accurate. So either we reject the null hypothesis or we fail to reject the null hypothesis and accept it because we have just failed to reject it. Another important thing you should understand, please mind that we don't know here, after solving a hypothesis testing problem, we still don't know which one of the two hypotheses is true and which is false. So we did not know before solving this problem, and we don't know after we have solved it. So what we know is just which one of the two hypotheses is more likely to be true. So and this affects the answer we are giving. So we don't say HO is true or HO is false. We don't say that the null hypothesis is true or the alternative hypothesis is true. We don't know. We still don't know. We just say we accept or we reject. So we have some reasons, and these reasons are just our observations. So our observations are such that we think that it's better to reject or to accept the hypothesis. So this is very important that you, very important just to understand, so that we don't give an answer to the question which of the two hypotheses is true. We give an answer to the question which of the two hypotheses is more likely, just when we have these observations. So are the observations, maybe it's better to say so, we're giving answer to the question, are these observations we have in favor of the null hypothesis or in favor of the alternative one? This is the point. Okay, and so this is just the what I have just told you. And the last thing, theoretical thing to be discussed is the p-value. So what is a p-value? So let me show you this picture one more time. So you see that, for example, you have calculated the value of the t statistic. And for example, this value falls to the acceptance region. But why it falls to the acceptance region? Because the border between the acceptance region and the critical region is as it is. And the border depends on alpha. As it is a quantile, and the level of the quantile depends on alpha. And alpha depends on your choice. And so you can change alpha, and by changing alpha, you can move the quantile. You can move the border between two regions, the acceptance region and the critical region. And you can move the border so that the border will be equal to the test statistic, to the capital T. So you can, by changing alpha, you can make the border between the acceptance region and the critical region be equal to the test statistic. And so in this situation, you won't be able to give an answer, as your decision depends on where the test statistic is, in the acceptance region or in the critical region. And if it is strictly on the border between the two regions, then you cannot make a decision. And so the p-value is this threshold value of the significance level. So the p-value is such a value that if alpha is less than the p-value, then the null hypothesis is accepted. And if alpha is greater than the p-value, then the null hypothesis is rejected. So the p-value is such a value that if you choose alpha less than p-value, then capital T will be in the acceptance region. So, and if you choose alpha greater than the p-value, then capital T will be in critical region. So, and in nowadays, when you solve a hypothesis testing problem, you usually give an answer in the form of the p-value. You usually don't say, I have chosen the significance level, like 0.05 or some else, and so that is why my answer is so that the null hypothesis is accepted or rejected at this significance level. But you usually present an answer as a p-value, and then you say you can choose the significance level and compare with the p-value. So this is the p-value, and then so for example, someone have asked you to test a hypothesis, and you tell him, so okay, I have tested it, the p-value is 0.07, for example. So, and now you are free to choose your own significance level, and so this means that for all significance level from 0 to 0.07, the null hypothesis will be accepted. And for all significance levels greater than 0.07, the null hypothesis will be rejected. So, and it's up to you to choose the significance level and to compare it with the p-value I have just found, and so and to make a decision. And so, for example, software that is used for hypothesis testing today, so there are many programs like SPSS, for example, or Statistica, so that are automatically solving hypothesis testing problems. So you just upload your observations, upload a table with observations, and then you choose a appropriate test. So you choose what you are going to test, what hypothesis you are going to test. You choose a test in the menu, you just press a button, and voila, the answer is here. And the answer such programs give is the p-value, not the answer. Like, they don't ask you for your significance level, and then they don't tell you like enter significance level, and then I'll tell you either your hypothesis is accepted or rejected, but they give you the p-value, and then you choose the significance level and compare with the p-value. So how we can find the p-value? So to find the p-value, you need to find the quantile of what level the value of the t-statistic is for the law distribution. And to find this, you need to have the CDF of the law distribution. So to find the p-value, you should know the CDF of the law distribution. If you have it, so you can find the p-value. And as in many hypothesis testing problems, so the law distribution is one of these popular distributions like standard normal or chi-squared or t-distribution. So you have the CDFs. For the standard normal CDF, you have this table, and for the other statistical distribution like chi-squared, Fisher, student distributions, you don't have the tables of the CDF, but you have the CDF in these programming tools for mathematicians. So in MATLAB, Maple, Python, and so on, we have these functions, CDFs of the popular distributions. So we need to find the p-values. So that's all with the theory for today. Now let's solve an example.